if you are working in machine learning or data science right now, you know that standard coding agents, things like Claude Code or Codex, they're just phenomenal at local engineering tasks, right?
Oh, absolutely. I mean, you point one of these systems at a localized bug, or you ask it to refactor a specific script, and it executes with an incredibly high level of technical proficiency.
Yeah.
It writes the code, it runs the tests, it squashes the bug.
Right. But, and I'm sure you've run into this, have you ever tried asking one of these state-of-the-art models to autonomously run a complex multi-day research project?
The wheels fall off almost immediately.
Easily.
Yeah, when you stretch the time horizon and increase the complexity of the objective, these agents completely lose the plot. They treat every single experiment in the queue as just an isolated trial. They completely lack the structural memory to retain the nuanced underlying reasons behind their previous failures, which leads to them operating in what we call basically diagnostic muddy waters.
Right? And welcome to the deep dive, by the way. Today we are exploring a framework that explicitly solves this exact memory bottleneck for long-horizon AI agents. We are dissecting a paper titled Toward Generalist Autonomous Research via Hypothesis Tree Refinement,
which was introduced by researchers from Renmin University of China and Microsoft Research.
Exactly. And the focus of our discussion is a system they've built and evaluated called Arbor.
Right, Arbor.
So our mission today is to unpack exactly how Arbor transitions AI from this sort of erratic sequential trial and error execution into a rigorous cumulative research process. And the engine driving all this is a concept called Hypothesis Tree Refinement, or HTR.
Yeah, HTR is the core of it.
Right. And to sort of set the stage for you listening, if you look at standard LLM agents today, their behavior can be likened to a panicked junior developer.
That's a great analogy.
Right. They desperately throw random Stack Overflow snippets at a bug, hoping anything compiles. It's a Markov-like process. The next action really only depends on the immediate, localized current state. Arbor, by contrast, operates like a senior principal engineer. It maintains a persistent, evolving mental map of the entire problem space, mapping out the dead ends, the promising leads, the underlying assumptions, before it delegates a single line of code.
To really appreciate the architecture of Arbor, though, we have to ground it in the specific operational problem it is designed to solve, which the researchers formalize as autonomous optimization, or AO.
Okay, let's unpack AO.
Mathematically, the researchers model this as a four-part system. So you start with a baseline piece of code or an artifact, which we'll call M0.
M0, got it.
Then you give the system a clear research objective, which is O. And then, and this is crucial, you set up two separate evaluators.
Two of them.
Yeah. A development evaluator, eDev, to guide the agent during its search, and a locked-away test evaluator, eTest, to keep it honest at the very end.
Okay, so M0 could be like a baseline NanoGPT training script or maybe a complex data synthesis pipeline. And the objective is to optimize that script. But I want to push back on this premise for a second.
Sure.
If you give an LLM this setup and just let it run for 48 hours, optimizing against that development evaluator, that eDev signal, isn't it essentially just p-hacking its way to a high score?
Oh, 100%.
Because we've all seen models find weird idiosyncrasies in a dev set and just exploit them without actually improving the underlying logic.
Exactly. Standard agentic loops are uniquely prone to that exact failure mode. The paper actually refers to it as silent metric chasing.
Silent metric chasing.
Yeah. In traditional ML, overfitting usually involves a model memorizing the training data by adjusting numerical weights, right?
Right.
But in agentic coding, the agent overfits the architecture or the logic itself to the specific edge cases of the development set. So it might drastically improve the development score, but when you run that final optimized artifact against the held-out test evaluator,
the performance absolutely collapses.
Completely collapses.
Because it didn't engineer a generalizable solution, it just memorized the specific constraints of the dev environment.
Exactly. The standard agent uses the development feedback signal to blindly navigate without learning any transferable principles. And this is exactly why Arbor introduces a strict physical separation between exploratory feedback and final artifact admission.
Okay.
And that physical separation is managed by Arbor's core innovation, the hypothesis tree.
Right, because if flat trial and error leads to pie hacking and forgotten failures, You have to give the AI a persistent memory structure, right? So Arbor's answer is to externalize the entire research state into this literal data structure.
Right. It completely replaces the standard linear chat transcript that most conversational agents rely on. The tree becomes the single authoritative source of truth for the entire optimization run.
So how is the tree structured?
Well, the root node represents the initial problem and that M0 baseline artifact. As you move down to depth 1 nodes, you find broad research directions. And then moving deeper into the leaves, the nodes represent highly specific, executable interventions.
But wait, a tree of raw batch commands or like sequential tool calls would be totally useless for higher order reasoning. I mean, it would just be a glorified log file.
Yeah.
These nodes have to contain some sort of abstractions, right?
Oh, they do. They absolutely do. Each node in the hypothesis tree binds together 3 distinct semantic fields to create that abstraction.
Okay, what are the fields?
First, you have the hypothesis itself. This must be a verifiable or falsifiable claim about how the code base should be altered to improve the objective.
Okay, so for example, if we disable weight tying between the embedding and unembedding layers, the freed capacity will be absorbed by the attention mechanism, improving perplexity. Like, that is a testable bounded claim.
Exactly. That's a perfect hypothesis. The second field is the metadata. This tracks the execution status, the numerical score returned from the development evaluator, and crucially, a literal Git branch reference.
A Git branch reference.
Yeah, pointing to the specific code implementation for that node. Because the system needs to know exactly where the code for this idea lives.
Makes sense. And the third field?
The third field is really the engine of the whole system, the insight. The insight isn't just a copy-paste of the terminal output. It is a synthesized, reusable interpretation of the experimental evidence generated by the LLM.
Okay.
It summarizes what was tried, what the empirical result was, and most importantly, why that result either supports or weakens the original hypothesis.
Oh, wow. So when you look at these 3 fields operating together, it really sounds like the hypothesis tree is essentially a Git version control system. But instead of just tracking code diffs and lines of text, Arbor is tracking the evolution of ideas and falsifications.
Exactly.
It's basically version control for the scientific method.
That's a great way to put it. The tree actively preserves the branching structure of research. When a hypothesis fails, the branch isn't deleted from the AI's context window. It remains permanently in the tree as a negative constraint. Future ideation is conditioned on that failure, ensuring the system knows never to attempt that specific mechanism again.
But a data structure is just a passive object, though. Like, you can design the most elegant tree in the world, but it is totally useless without a system to manage it and run the actual experiments. How does Arbor operationalize this tree without falling back into the trap of letting a single agent just run wild?
So Arbor handles this by fundamentally splitting the AI's identity into 2 completely distinct roles, the coordinator and the executors.
Yeah.
This dual architecture is what allows it to balance global strategy with local execution. It totally prevents the agent from getting lost in the weeds of debugging.
Okay, let's look at the coordinator first. This is the principal engineer making the mental map, right?
Right. The coordinator is a long-lived process that owns the global hypothesis tree. It maintains the overarching research strategy, deciding which branches to explore, which to merge, which to prune. But the critical invariant here is that the coordinator never edits the target directly.
Wait, really?
Never. It explicitly does not have access to file writing tools for the main repository.
That's a massive architectural shift.
Yeah.
I mean, in almost every other agentic framework, the entity making the plan is the exact same entity writing the code and reading the error logs.
And that's exactly the problem. By enforcing a hard boundary at the tool level, Arbor prevents the coordinator from making undocumented, sneaky little code tweaks that aren't tied to a formal hypothesis.
Oh, I see.
Because if you let the planning agent write code, it will inevitably start hacking away at bugs just to fix a broken script, and suddenly the code no longer reflects the hypothesis it was supposed to be testing.
Right.
Every single code change must be delegated.
And that delegation goes to the short-lived executors. So whenever the coordinator decides to test a hypothesis, it spawns an executor. And what's fascinating is that it spawns them in completely isolated Git work trees.
Yes.
Like they are physically sandboxed from each other and from the main code base.
Yeah, exactly. An executor is handed a fixed hypothesis, the accumulated insights from its ancestor nodes, so it has context, and the command to run the development evaluator. Its only job is to implement that specific idea, test it, and report back the score and the insight. It cannot see what other executors are doing, and it has absolutely no access to the global tree.
Okay, let's explore the friction there, though. Because if an executor is sandboxed and hits a wall mid-implementation, say the metric completely stalls out, or the code requires a major refactor just to compile, why can't it just pivot to a new idea? I mean, as human engineers, if our approach fails halfway through, we pivot. Engineering flexibility is usually considered a good thing, isn't it?
It is a natural instinct, sure, but Arbor enforces a strict hypothesis-bound rule for a very specific mathematical reason. If an executor secretly pivots when a metric stalls and tries a different approach just to get the code working,
Yeah.
the final development score and the code it returns no longer map to the original hypothesis assigned to that node.
Oh, right. It totally breaks the semantic meaning of the tree. The coordinator would look at the node and think it's evaluating hypothesis A, but the executor actually implemented hypothesis B to get the code to run.
Precisely. The insight back-propagated to the coordinator would be completely corrupt. The global strategy would be updated based on false premises. So by enforcing strict isolation and the hypothesis-bound rule, Arbor guarantees that the experimental evidence is always verifiable and correctly attributed.
Okay, I get it.
If the idea underperforms after a good faith implementation, that failure is the exact finding that needs to be reported. You sacrifice a little bit of local scrappiness to ensure the absolute global integrity of the research data.
Okay, so we have the coordinator managing the tree and the isolated executors doing the implementation. Rather than walking through this like a table of contents, let's picture how this actually unfolds over hundreds of turns.
Let's do it.
Imagine the coordinator waking up at the start of a cycle. Its first job isn't to code, it just observes the tree. It reads the structured projection of active frontiers, the validated findings, the pruned constraints. It basically grounds itself in the actual data of what has happened so far.
Right. And once it observes the state of the board, it moves into step 2, ideation. The coordinator selects a promising parent node and proposes new child hypotheses under it.
Okay.
Because it just observed the tree, these proposals are deeply conditioned on accumulated evidence. It won't suggest a mechanism that a sibling node just proved to be ineffective a few hours ago.
Because it remembers. After brainstorming, step 3 is select. The coordinator looks at all the pending leaf nodes across the tree and calculates expected utility based on prior evidence. It selects the most promising ones, and then step 4, it dispatches them.
Yes, dispatch.
And because of that Git worktree isolation we talk about, it can dispatch 4 or 5 different hypotheses to parallel executors simultaneously without any code collisions.
Exactly. So the executors go to work in their isolated sandboxes, running their trials against the development evaluator. When they finish, they return a structured report to the coordinator containing the factual results, the numerical score, and their distilled insight.
Right.
And this leads to step 5, the most critical phase of the entire framework, the backpropagation of insights.
I want to spend some time here because this is really where the magic happens. The coordinator takes that structured report and writes the data into a leaf node. But it doesn't stop there, right?
Right.
It then takes that text-based insight and abstracts it upward through the tree.
Yes. It synthesizes the insights of the child nodes to update the parent node and updates the parents to update the global priors at the root.
So cool.
The LLM is explicitly prompted to look at the local failure, say an executor reporting that a specific data augmentation technique caused a memory leak, and rewrite that into a generalized conceptual constraint for the parent node.
Right, so if we look at this mechanically, it is basically backpropagation applied to the scientific method. Like in a neural network, you backpropagate the numerical error gradient from the output layer to update the weights in the hidden layers. In Arbor, you are backpropagating empirical failures and successes from the leaf nodes to update the conceptual constraints of the research space. Instead of updating a numerical matrix, Arbor is updating the AI's semantic understanding of the physics of the problem.
That is spot on. A local observation at a leaf node like a data interface mismatch propagates upward and becomes a direction-level constraint. So when the coordinator wakes up for the next cycle and observes the tree, that constraint actively shapes the global ideation.
It fundamentally alters the probability distribution of what the AI will suggest next.
Exactly, ensuring the system structurally cannot repeat the same mistakes.
Okay, so that's 5 steps. And once this cycle runs and a candidate artifact actually achieves a high score on the development evaluator, we hit step 6. The final defense against p-hacking, the decide step, or the merge gate.
Right, the merge gate. Promotion to the main code base is guarded by a ruthless, held-out merge gate.
Ruthless. I love that.
It is. The candidate artifact is placed in a fresh, completely detached work tree. It is then evaluated on the held-out test evaluator. It is only merged into the main trunk if it improves that held-out score.
Right.
This physically separates exploratory success on the development set from verified, generalized progress.
It's a brutal filter. If an executor brings back a high development score but a low test score, the artifact is just rejected. The node is retained in the tree as evidence of an overfitted dead end, but the code is kept out of the main repository. It forces the system to find robust solutions.
Yeah, exactly.
So the elegance of the dual architecture, the git isolation, the backpropagation of insights, it's super compelling on paper. But the researchers needed to prove that this actually outperforms standard single-agent loops on expert-level tasks.
Right. And they did.
Let's look at the empirical results. They tested Arbor on 6 real-world autonomous optimization tasks. And these weren't toy problems.
No, not at all.
They included complex model training, like finding the optimal hyperparameter schedule for NanoGPT. They tackled harness engineering, specifically improving the search logic for web browsing agents in a benchmark called BrowseComp. And they optimized data synthesis pipelines.
And they set up an incredibly rigorous baseline comparison. They pitted Arbor directly against Codex and Claude Code. They provided all the systems with the exact same initial artifact, the exact same development and test evaluators, and the exact same resource budget, a strict 48-hour wall clock limit.
So it's a totally apples-to-apples comparison of compute and time constraints.
Yes.
You'd think a state-of-the-art agent like Claude Code would put up a massive fight given 48 hours to optimize a script. How did Arbor stack up?
Arbor achieved the best held-out result on all 6 tasks.
Wow.
Not just on the development set, but on the held-out test metrics, which proves it wasn't just p-hacking. On average, Arbor attained more than 2.5 times the relative held-out gain of Codex and Claude Code.
2.5 times the gain is a massive leap in capability. And they also ran it against industry-standard benchmarks, right?
Yeah, they evaluated Arbor on MLE-Bench Lite, which is an established benchmark for machine learning engineering tasks. Using GPT 5.5 as the backbone model for both the coordinator and the executors, Arbor reached an 86.36% any medal rate.
That's wild.
That was the absolute strongest result in their entire comparison pool.
Okay, the numbers are undeniable, but as machine learning practitioners, we have to ask why it performed so well. Was it purely because it was organizing experiments into a tree structure? The inflation studies in the paper are incredibly revealing on this point. They systematically stripped away components of Arbor to isolate their impact.
Right. When they removed the tree structure entirely, reducing the search to a flat sequential experiment queue attached to the root, the performance dropped significantly.
Right.
On ML-Bench Lite, the any medal rate fell from over 86% down to about 63%.
Okay, so the hierarchy clearly matters. But the second ablation is what I find most fascinating. What happens if you keep the hypothesis tree, but you turn off the inside backpropagation? You let the executors report back to the leaf nodes, but you don't synthesize those text logs into conceptual constraints that update the parent nodes.
When they disabled the upward propagation of distilled lessons, meaning local leaf results stayed isolated at the bottom of the tree, the performance suffered an even steeper drop, plummeting to a 54.54% any medal rate.
Wait, keeping the tree but losing the backpropagation of insights is actually worse than losing the tree entirely.
Yes. It proves a fundamental point about autonomous research. A tree structure without propagated lessons can organize experiments syntactically, acting as a complex filing cabinet, but it provides zero semantic memory for future decisions.
Wow. Hierarchy alone is just syntax. The true engine of autonomous research is the semantic memory. It is that specific mechanical ability to prompt an LLM to turn local, isolated execution logs into global constraints so the AI actually learns and evolves its served space rather than just brute forcing the dev set.
Exactly. The trace logs from the BrowseComp task illustrate this perfectly. BrowseComp involves optimizing the logic for web browsing agents.
Right.
Arbor's early experiments proved that fine-grained answer verification was effective, but the total coverage of the web pages was a bottleneck.
Good.
It tried several variants, failed, and generated a specific insight. It needed a mechanism to share evidence across browsing trajectories without actually merging the trajectories themselves. The final, successful artifact was a direct logical consequence of those accumulated backpropagated constraints.
It reasoned its way to the architecture through falsification. It didn't just guess it or stumble upon it via random token generation. It turned transient execution traces into a persistent research state.
Exactly. The framework successfully transitions the AI from a tactical coder to a strategic researcher.
Let's bring this all together. We've explored how Arbor utilizes hypothesis tree refinement to solve the critical memory bottlenecks of autonomous optimization. By fundamentally separating the long-lived coordinator from the isolated short-lived executors, and by enforcing strict insight backpropagation guarded by a ruthless, held-out merge gate. Arbor turns erratic trial and error into a rigorous, cumulative scientific process.
It demonstrates that for an AI to conduct genuine generalist research, it requires an explicit auditable memory of its own failures, organized in a way that mathematically constrains its future actions.
It's incredible. But I want to leave you, the listener, with a final provocative thought to mull over. We've seen that Arbor can successfully use this hypothesis tree to autonomously engineer better machine learning algorithms, optimize model training schedules, and refine complex data synthesis pipelines. The coordinator manages the tree, the executors write the code in sandboxes, and the system improves the target artifact.
Yeah.
But what happens when you make the target artifact, Arbor itself?
Oh, wow. Applying the autonomous optimization tuple to the optimization framework itself is a staggering implication.
What happens when you point Arbor at its own code base? Could this exact same tree structure be used to recursively refine the Arbor framework? Imagine an AI researcher that uses backpropagated insights to autonomously rewrite and optimize its own scientific method.
Right, because if Arbor can optimize a search harness for a web browsing agent, it could theoretically optimize the very prompts and algorithms it uses to select hypotheses and synthesize insights.
Exactly. We started this deep dive by comparing standard AI agents to junior developers throwing code at a wall, and Arbor to the senior principal engineer who builds a mental map before acting. But if Arbor can point its hypothesis tree at its own architecture, we aren't just looking at a principal engineer anymore. We're looking at a principal engineer who is simultaneously running controlled experiments on how to write the textbook on being a better principal engineer. And that is a fascinating horizon for the future of autonomous research.